Okay, welcome to Chapter 5, Part 1, where we start talking about friction and drag. So we're going to start with friction and drag, and then Part 2, we'll talk about elasticity. So what is friction? Well, we all know what friction is at some level. But if you really look at a surface, let's say we look at a surface at the microscopic level, it's not actually smooth. Even the desktop, which feels somewhat smooth to us, is not actually smooth. It's actually got all this structure to it at the microscopic level. And so when something like this box is sitting on a table, all these little pieces tend to interlock, right? All those little pieces are sort of holding this together so that you can't slide it easily. So that's static friction, right? The friction of this interlocking bits with the material. Now, if you push on this and you get it moving, and then you can kind of imagine, instead of interlocking, now this is sort of, the top part is sort of bumping along on top of the bottom part. So there's still friction because you're still hitting it and you're still having to go over obstacles, but it's not as bad as the static friction, right? So we have two kinds of friction that we talk about. We talk about static friction, friction that happens when you're sitting still, and kinetic friction, friction that happens when you're in motion. Those are the two different kinds of friction we talk about. All right. In static friction right here is always less than or equal to what we call the coefficient of static friction mu s. That's a Greek letter mu sub s. So it's always less than or equal to mu sub s times the normal force. Now, if it was me sitting here on top of this, or standing here on top of this, the normal force is equal to my weight, right? So the normal force in that case is just mg. Now, if I'm on a slope, right, if I'm on a slope and I'm trying to stand up on a slope, well, the normal force is a little bit different there, and we'll have some problems when we talk about it because the normal force is straight out, right? Normal force is straight out from the surface. So that is a little different from the normal force when it's straight down. So here you are again, static friction, right? Static friction, the friction that occurs when you're sitting still. Static means not moving, right? Are in a fixed state. So the static friction is always less than or equal to the coefficient of static friction times the normal force. Okay. Now, the kinetic friction, all right, looks similar, a little different. Up here, static friction always less than or equal to, kinetic friction is strictly equal to the coefficient of kinetic friction times the normal force. So, okay, let's look at that or think about that for just a moment. Both of these are a coefficient times the normal force. So, if I weigh more, right? Or let's say I've got a light box I put on this versus a heavy box that's like completely full of stuff, right? The friction for this is probably higher than the friction for this, simply because the normal force with all the stuff in the box makes all the stuff in the box makes the normal force higher. Because normal force is higher, friction is higher. And then this doesn't matter. I mean, if it's kinetic or static, that's still true. The other thing we have here of the two types of friction is that static friction is always greater than kinetic friction. Think about that for a minute. If kinetic friction were the same as static friction, right, then when I got to the point where I was supposed to be able to just move this, I wouldn't be able to. If kinetic friction was higher than static friction, then I get to the point where it's supposed to move, but it wouldn't, right? I mean, so static friction always has to be greater than kinetic friction. The other thing to pay attention to, back to the less than or equal to sign here, right? So static friction is this is the maximum static friction can be. If I'm not pushing, if I got a box up here and it's a really bad box. So if I got a box up here and I'm pushing on it, but I'm pushing on it less than this amount, less than US times the normal force, then static friction only counteracts it. Static friction is never going to be greater than the force I'm applying. All right? Because if static friction were greater than the force I'm trying to move the box with, the box would scoot this way because of friction. That makes no sense, right? So static friction is always less than or equal to the normal force times the coefficient of static friction. So what does this coefficient look like? Right? So for most material, then, and it depends on, you'll see two things here. In the system, we call it the system, it depends on the two different materials involved. So here we have rubber on dry concrete. So coefficient of static friction 1, and then coefficient of kinetic friction 0.7, right? And then rubber on wet concrete, coefficient of static friction 0.7, coefficient of kinetic friction 0.5. How do you get these? You have to measure this, right? You just have to go out and you have to measure it. You cannot, we don't have the techniques to actually accurately calculate this, right? And there are some things though that make sense, like shoes on ice, 0.1 for static and 0.05 for kinetic, right? If you're standing still, if you're on ice and you start to slip, you tend to stand still for a minute. Why? Because then you're using static friction to get your balance. And then you try and move again where you have less friction working for you. All right? Steel on ice on ice, all these different materials, steel on steel, all these different materials, you have to go out, you have to measure what the coefficient of friction is in order to put it in this table, right? We don't go out and calculate this from anywhere. We have to measure this. Or we have to use equations like this. Well, we do use equations like this to figure out what the coefficient of friction is. We'll measure the frictional force, we'll measure the normal force, and then we'll figure that out. Next bit of friction is drag. So drag is what happens when an object moves through a fluid. And we often forget that air is a fluid, and that when planes go through air, they have experienced drag. When you drop things in air, they experience drag. Drag forces increase the square of the speed, right? So when you double the velocity of your car, you're going down the highway and you double the velocity of your car, the drag force, the amount of force you have to overcome just to keep moving, goes up by a factor of 4, right? So your fuel efficiency isn't great when you're going fast. Your fuel efficiency is better when you're going slow because you're not having to work as hard to push yourself through the air. Drag force is this simple formula. Now, I know it looks like a lot of stuff, but it's just got simple things in it that we have to measure in one way or another. So the drag force, right? It's 1/2 of the drag coefficient. Okay. Drag coefficient, you have to look up in a table. Drag coefficient has to do with the shape of an object, right? Rho is the density of the fluid. So the density of air is much denser than you would think it would be. It's about 1.3 kilograms per cubic meter. We don't think of air as having much weight, but 1.3 kilos per cubic meter, that's actually non-trivial, right? So we have the drag coefficient, we have the density of the material you're going through, the fluid you're going through. We have the surface area of the object facing the fluid, right? So, if you're going that way, right? I've got a box. The surface area on this end that's facing the fluid is what's matter. Or if I have a ball, right? If I have a ball, not a very good ball. If I have a ball, then we're talking about really a circle, right? Because if you look at it from the air, if I have a ball and it's coming at me, I see a circle. If the ball is coming at me, I see it as a circle. The drag coefficient takes into account the shape, right? The area takes into account the size. And then last on here, after area, is the velocity. And this all goes as velocity squared. All right, all goes as velocity squared. So if we were to look at a few drag coefficients, let's look at a few drag coefficients. Here we go. An airfoil, which is basically a wing, right? A wing of a plane, 0.05. Toyota Camry, 0.28. Ford Focus, 0.32. Honda Civic, 0.36. Ferrari Testarossa isn't actually all that good, right? 0.37. Dodge Ram pickup, 0.4. A Sphere, 0.45. Hummer 2, 0.64. A skydiver feet first, all right, 0.7. A bicycle, 0.9. A skydiver horizontal, 1. A circular flat plate, 1.12, right? Circular flat plate, or we could even think of this as kind of like a piece of paper too, a piece of paper similar to this. Skydiver, skydiver is we will talk about in the problems, we'll talk about terminal velocity, right? So what's terminal velocity? Well, let me go back here. So your weight when you're skydiving, your weight is mg. It doesn't matter that you're falling. Why are you falling? All right. Ooh, that's a really bad G. You're falling because gravity is pulling down on you, right? Now, what's pushing up on you? All right. What's pushing up on you is the drag force. So you have mg pushing down, and you have the drag force, right? The drag force pushing up, because the drag force, it's a frictional force, right? Or like friction, it's resisting your motion, so it's pushing up. Well, when you get to the point where mg, you're going fast enough, you're eventually going to get there, right? When mg equals the drag force, at that point, you've reached what we call terminal velocity. You're no longer going to accelerate. Why? All the forces balance. F net is 0. Because F net is 0, the acceleration at that point, all right, acceleration at that point is 0. We call this terminal velocity. For a human skydiver falling through air, terminal velocity is around 125 miles an hour. For a mouse falling through air, I'm not going to try even drawing a mouse. For a mouse falling through air, terminal velocity is so low. A mouse hits terminal velocity essentially within the first couple of meters. It can survive that fall. What that really means is you can drop a mouse as far as you want and it will be just fine. This experiment was actually done. They dropped a mouse 1,000 meters, a full kilometer. Mouse hits the bottom, squeaks, runs away, because it has reached its terminal velocity and it can survive that. Once it's reached terminal velocity, it will not go any faster. All right, that's it for part 1. I'll see you soon in part 2.